I created the cleanest and most customizable outline shader I could in Unreal Engine 5, and I'm going to teach you not only how to recreate it from scratch, but also how to understand every part of it so that you can go from this to this. By the end of this video, you'll be able to change the thickness of the outline strokes, you'll be able to change their color, here. You'll also be able to apply the outline shader effect only on some of the actors of the scene, like you can see right here. You'll be able to modulate the thickness of these strokes so that they become thinner when an object is far away from the camera and thicker when it's close to the camera. You'll be able to prevent the strokes from being drawn on things that are too far away, like this cube and this sphere right here. You'll also be able to limit the artifacts that appear on the surface when the camera view is nearly parallel to it, like you can see right here. This is an effect that you can see on most of the shader that you can find on the internet. I will show you how to prevent this from happening. And last but not least, I'm going to show you how to do this. You will be able to select any actor of the scene and change its outlines color. With this tool, you'll be able to have infinite multicolored outlines. The outline shader we are going to create here with Unreal Engine 5 is a post-process effect that will analyze the scene texture, in other words, what is shown on screen, to detect edges in the scene and draw outlines on them. The edge detection process is pretty simple to understand and will work as follows. First, for each pixel of the screen, we are going to get its left, right, up and down neighbors. Then we are going to sample the depth of each of these 5 pixels and use this formula to calculate the depth variation rate that occurs around the current pixel. As you can see here, the more the depth varies around a given pixel, the bigger the result of this variation rate formula will be. Once the variation rate is calculated, all we need to do is compare its value to a given threshold, and if the variation rate is bigger than the threshold, this means that the depth varies a lot around this pixel, and therefore we can change its color to black to materialize an outline on this pixel. Okay, that's great, but if we only apply this edge detection method to our scene, we'll quickly see that our outline shader won't be able to detect some of the edges, like these ones, for example, that are located at places where depth doesn't vary a lot. To address this issue, we are going to combine our depth edge detection method with a normal edge detection method, which this time, as its name suggests, will be based on sampling the normals of a pixel and its 4 neighbors. I won't go into detail here, but just so you know, we are going to apply this formula, which will give us the normals variation rate, in other words, the orientation variation rate of the surface around the current pixel. Then, just like with the first edge detection method, if this normals variation rate is bigger than a given threshold, we'll change the color of the pixel to show that there's an outline there. Finally, once we have our depth edge detection method and our normal edge detection method, we can mix these 2 methods together to detect a lot more edges in the scene. Okay, so now that you know the gist of how our outline shader will work, we can start implementing it by creating a post-process material that will allow us to apply our effect to the scene. Oh, and before I forget, if you're a Patreon, you have access to the final Unreal Engine 5 project with all the useful comments to understand how the shader works. So here, back to my project, I'm going to right-click and create a new folder called Post-Process. I'm going to open it. Then here, I'm going to right-click, select Material to create a new material. I'm going to rename it to pp_outline shader for Post-Process Outline Shader. I'm going to open it. Then here, in the Details tab, on the left side of the interface, I'm going to select in Material Domain, I'm going to select Post-Process. Then I'm going to go down, search for Blendable Location, right here, Blendable Location. I'm going to select Before Tone Mapping. So here we tell Unreal Engine 5 that we want our post-process effect to occur before adjusting the colors with the tone mapper. I won't go into detail here, but just so you know, if you leave this parameter to after tone mapping, this will make the outlines shake. So here I'm going to save, then I'm going to apply. I'm going to go to my content, right-click on my PP outline shader, select Create Material Instance. I'm going to rename it to PPI for Post-Process Instance Outline Shader, and doing this will allow us to modify the parameter of the shader and see the result in the viewport without having to recompile the material. So here I'm going to apply this post-process material to the scene, and to do so we need to assign it to a post-process volume that is placed in the scene. I'm going to add a post-process volume by going here. I'm going to click on it, select volumes, and then select post-process volume right here. Then, while having the post-process volume selected in the viewport, you're going to go to the Details tab right here. You're going to search for material. And here you have post-process material array. You're going to click on the plus sign, select Asset Reference. And here in my content, I'm going to select the PPI outline shader and assign it by clicking on the arrow right here. Now you can see that the effect is not applied to the scene, but if you go in the post-process volume, you see that everything turns black, which means that our effect is applied only when you go in the post-process volume. To apply it to the entire scene, you have to search for Infinite and check the option Infinite Extent. This will apply the effect to the entire scene and not to the things that are inside the post-process volume. As you can see, as soon as we apply our outline shader to the scene, it becomes completely black. This is totally normal, since when Unreal Engine 5 is done processing the final render of the scene, before showing it on the screen, it sends this render to the graphics pipeline down to our post-process shader, which then applies some modifications to it and sends it back in the graphics pipeline so that it can be shown on screen. So here I'm going to open the outline shader. And of course, this is a simplified version of the process, but knowing this and seeing that our post-process material returns nothing, I think you'll understand why our screen goes completely black. To address this problem, and before moving on to the next part of this tutorial, we are going to turn our post-process effect into what we call a pass-through post-process effect, which does nothing to the render of the scene and display it as is to the screen. To do so, we are going to use a node called Scene Texture, which allows us to sample the textures that are sent to our shader before being displayed on screen. So here I'm going to right-click, type Scene Texture, select this node right here, the Scene Texture node. And here, when I select the Scene Texture and go to the Details panel, we can see the various textures that are created by Unreal Engine 5 and that we have access to. We'll use some of these textures later in this video, but for now, let's set it to the post-process input 0, so this option, to get the look of the scene as it is supposed to appear on screen. Then here, I'm going to connect the color pin to the emissive color pin right here. I'm going to save and apply. And if we go back to the viewport, you will see that everything went back to normal, as if there was nothing applied to the final look of the scene. Now that we've set up our base shader, we can move on to the next part of this tutorial and start modifying our effect to add outlines to the scene. Okay, so now that we can access the scene texture processed by Unreal Engine 5, we are going to create a material function that allows us to get the current pixel and its up, down, left, and right neighbors. So here I'm in the post-process folder. I'm going to right-click, select New Folder, and call it Functions. In this folder, I'm going to right-click, select Material, and then select Material Function right here. I'm going to rename it to MF for Material Function _ get kernel, because we are getting the pixels of the convolution kernel, and then I'm going to open it. So here, since this material function is going to return the coordinates of the current pixel and its neighbors, we are going to add outputs for each of these pixels. So here I'm going to rename the output result to center by going over here, center. Then I'm going to select it and press Ctrl+D on my keyboard to duplicate it. I'm going to rename it to left. Change the sort priority to 1 right here. Then I'm going to duplicate it. Here, I'm going to rename it to right. Sort priority of 2. Duplicate it. I'm going to rename it to up. Sort priority, I'm going to set it to 3. And duplicate it one last time. Rename it to down. And change its sort priority to 4. So here we have outputs for each of the neighbors of the current pixel. So here, as for the inputs, we are going to add only one, which will represent the thickness of the outlines strokes we want to draw. So here I'm going to right-click, type function input. I'm going to change its input type to scalar, since it's a simple number that will express the outlines thickness that we want. I'm going to rename it to width here. So I won't go into detail about it, but just so you know, when detecting edges, the farther we search for neighbors around the current pixel, the bigger the outlines will be. So here I'm going to press 1 on my keyboard and click to add a constant. I'm going to connect it right here. I'm going to change its value to 1. And now we can start implementing it. So here, the easiest pixel from which we can get the coordinates is the current pixel. So here I'm going to right click, type texture coordinate, get this one. I'm going to connect it right here. Then, now that we have the coordinate of the center pixel, let's try to find the coordinates of its right neighbor, this one. First, we need to create a horizontal offset. So I'm going to right click, type constant and select constant to vector. I'm going to set its R value to 1, and I'm going to add a comment called horizontal offset. By setting its value to 1, its R value to 1, we create an offset to the right. This constant holds the direction we need to go to make an offset to the right. And now to determine how far we want to search for a neighbor, we are going to multiply this direction by the input width. So here I'm going to select this. I'm going to add a multiply node. Here I'm going to connect it right here. Then, before adding this offset to the coordinates of the current pixel, we need to multiply it by the size of the pixel on screen. So here I'm going to multiply, and I'm going to get the scene texel size. This represents the size of a pixel on screen. Why do we need to do this? It's because if you have a 1080p resolution on your 4K monitor, a pixel will be bigger than if you had the same resolution on a 720p monitor. So finally, once it's done, we can multiply this by -1 to create an offset to the left, and then add these two values to the center coordinates to get its neighbors. So here I'm going to get the coordinates of the center pixel. I'm going to add the offset that we've calculated, then multiplied by -1 to get the left neighbor. And then I'm going to add the same coordinate without a -1 multiplication here to get the right neighbor. And there we go. So now that we know how to get the coordinates of the left and right neighbors, we can apply the same method to get the up and down neighbors. So here I'm going to select all of these, press Ctrl+D on my keyboard. Then here for the horizontal offset, I'm going to put the R value to 0 and the G value to 1 so that we have a vertical offset. So this offset goes to the bottom. So this is the neighbor from the bottom of the current pixel. So here I'm going to multiply by the width to know how far we want to search for a neighbor. Then I am going to multiply by the size of the pixel on screen. And finally, I'm going to multiply by -1 to get the up neighbor here. And then I'm going to get the same result without -1 multiplication to get the down neighbor. And voila! Now that we can get the convolution kernel, we can move on to the implementation of the depth edge detection method. Okay, so back in my content browser, in my functions folder, I'm going to right-click, create a new material function by going to materials and select material function. I'm going to rename it to MF for material function underscore detect edges underscore depth. Then I'm going to open it. And this function will apply the formula we saw earlier and will return a value of 1 if the current pixel is on an edge and 0 if it's not. So first we need to create two inputs. So I'm going to right click, function input. I'm going to rename it to thickness, change its type to scalar. I'm going to put a constant of 1 to say that we want outlines of size 1 pixel. And this input represents the desired thickness for the outline strokes. Then we are going to create another input, right-click, function, select function input, set it to scalar 2, and change its name to threshold. I'm going to add another constant. This time I'm going to put a value of 4. And this input represents the threshold to which we are going to compare the result of our formula. And as a reminder, if the result is greater than the threshold, the current pixel is on an edge. Okay, so now that we have everything we need, we can apply the formula we saw earlier. So here, I'm going to apply everything we saw from the slides earlier. I'm going to select in my post-process functions, I'm going to get kernel. I pressed Control and space for information so that you can summon the content browser, Control space. I'm going to get the mf_get kernel. I'm going to drag it in my graph. Then in the width input, I'm going to plug the thickness input of my material function. And here I'm going to sample the depth of each of the pixels. So here I'm going to right click, select scene depth. I'm going to duplicate it 4 times so that we have 5. I'm going to sample the scene depth of the center pixel, the left pixel, the right pixel, the up pixel, and the down pixel. Then the formula says that we need to multiply the depth of the center by 4. Here, I'm going to multiply it by 4. And we need to add the scene depth of all the neighbors together. Here, press Ctrl plus D to duplicate. Here, Ctrl plus D. And finally, if we subtract this value by the scene depth of the center pixel multiplied by 4 and apply an absolute node to this, we get the formula we saw earlier. So here the scene depth node allows us to sample the depth of a specific pixel based on its coordinates. So here we have the main version of the formula that I've shown you earlier, which will draw outlines at the center of an edge. I'm going to take it a bit further by showing you how to draw inside and outside outline strokes. So you'll see the modification we need to apply are pretty simple. Here, all I have to do is that I need to delete the abs node. Here, I'm going to get the subtract and put it over here. And here, I'm going to duplicate it, put the multiply 4 on the A and this one on the B. So you have one where you subtract this value by this value, and one where you subtract this value by this value. Then here, I'm going to right-click, type switch parameter. I'm going to rename it to inside strokes depth outlines. I'm going to duplicate it and rename it to outside strokes depth outlines. Here I'm going to add a constant, type constant. I'm going to plug this value of 0 in the false pin of both the switch parameters and plug this into the outside strokes and this into the inside strokes. Then what I have to do is that I have to get the max node here and plug it right here, like this. Okay? So here I've added parameters that will appear in the post-process material instance, PPI outline shader, that we created earlier. To show both types of strokes by default, we are going to change their default value to true. So I'm going to select both of them. And here, the default value, I'm going to check it. You will see that this will turn to true right here. And now that we have the result of our formula, we just need to compare this to the threshold. So I'm going to get the input threshold right here. And I'm going to add a step node. Right-click, step. Then I'm going to plug the max into the X input and the threshold into the Y input. And finally, plug the result into the output result. This will create an error, but don't mind it, it's a false positive. And what the step node will do is output a value of 1 if the result, so this, the result of this, is greater than the threshold. If it's not greater than the threshold, it will return 0. So all we have here is an edge detection method that works correctly. So this will return 1 if we have an outline and 0 if we don't have an outline on the current pixel. Okay, so now that our depth edge detection method function is done, we can call it in our outline shader. So I'm going to close this one, close the get kernel, and here in my PP outline shader, I'm going to drag, press Ctrl plus space on my keyboard, and drag the detect edges depth here. I'm going to right click, select promote to parameter, this one. Here I'm going to rename it to threshold depth outline. I'm going to put it to a value of 4. Then I'm going to right click on thickness, click on promote to parameter, rename it to thickness depth outlines, set it to a value of 2. And to visualize the result, we can connect the output to the emissive color of the parameter. Here, if I click save, as you can see here in the viewport, the edges are detected correctly since everything is black, except for the parts where there are outlines strokes. So you can go to the viewport, the main viewport, and you will see that it works correctly. So now if you want to apply the outlines above the default render of the scene, we are going to use a lerp node, linear interpolate. So here I'm going to right click, type linear, and select linear interpolate, this one. I'm going to plug it in here. The color, I'm going to plug it right here in the lerp. And the detect edges depth, I'm going to plug it in the alpha input. So here we tell Unreal Engine that for each pixel of the screen, if the alpha parameter of the lerp is equal to 0, which means that the edge detection didn't find any edge there, we can change its color to what's plugged into the A parameter of the lerp, which is the color of the pixel as it is sent to the shader. However, if the alpha equals 1, then we set its value to 1, which represents a white outline. So if we want to change the color of the stroke, we just need to plug a different color in the B parameter. So here I'm going to right-click, type vector parameter, this one. I'm going to rename it to color depth outlines. Then I'm going to plug it in the B, and you will get an error. So here we get an error that is due to the fact that the scene texture outputs a color composed of red, green, blue, and alpha, whereas in the color parameter that we created here, we just created it with only red, green, and blue colors. So to solve this error, we need to add a component mask. So here I'm going to drag a node here and type component mask, and we are going to mask out the alpha. Right here, you select red, green, blue. This will get the color from here, which is composed of red, green, blue, and alpha, and we remove the alpha parameter. So now if I plug it right here, you will see that we don't get the error anymore. Here, if you go to the viewport, you open the PPI outline shader. If you select the color depth outlines, click on it, and change its color to red, for example, you will see that the outlines of the scene become red. Okay, so now that our depth edge detection function is finished, we can implement our normals edge detection function. So here in my functions folder, I'm going to right click, select materials and material function. I'm going to rename it to mf_detect edges_normal. I'm going to open it. And just like with the depth edge detection function we created earlier, this function will return 1 if the current pixel is on an edge and 0 if it's not. So since the inputs are the same as the depth edge detection function, I'm just going to open it, press Ctrl plus space on my keyboard, open the depth edges detection depth. I'm going to select the two inputs, the threshold one and the thickness input, press Ctrl plus C on my keyboard, go to detect edges normal, press Ctrl plus V. This will paste here both the inputs, and I'm going to modify the preview value of the threshold to 1. Okay, so now we are going to apply the detection formula, but before doing so, we need to sample the normals of the current pixel and its neighbors. To do so, we are going to use the scene texture node we saw earlier. So here, I'm going to press Ctrl plus space, get the kernel, the convolution kernel. I'm going to plug the thickness into the width input. And here, I'm going to right-click, select scene texture. And here, in the scene texture ID, I'm going to select this time the world normal. This will get the normal map of the screen. So here, if I plug the center into the UVs, we are sampling the normal of the pixel that is placed at the center. So here I'm going to press Ctrl plus D to duplicate it 4 times. And here I'm going to sample the normal of the left neighbor, right neighbor, up neighbor, and down neighbor. So here, by setting the scene texture ID to world normal, we can sample the normal of a pixel based on its coordinates. Now, if you remember well, in order to apply the detection formula, we need to make the sum of the distances between the normal of the current pixel and the normals of its neighbors. So here, I'm going to get the center here. I'm going to type distance. I'm going to get utility distance right here. This one. I'm going to get it, duplicate it 4 times, 3 times, 2 times. World normal here, right here. I'm going to get the distance from the normal of the center pixel to the normal of the left pixel, the distance from the center pixel to the normal of the right, and etc. Here and here. Now that we get the distance from the normals of the center pixel to its neighbors one, I'm going to add them together. So here I'm going to type add, get this one, duplicate it, add these ones together, duplicate it again, and add this one. And finally, just like with the first edge detection method, we are going to compare this result to the threshold. So here I'm going to right-click, add a step node, plug it right here. So here, if you remember well, if the result of this formula is greater than the threshold, this will return 1. If not, this will return 0. So just a quick note, for this function, we are not going to implement the ability to get inside or outside strokes like we did with the depth edge detection method, because it's not useful. It's as simple as that. Okay, so now that our new edge detection method is done, we can implement it into our shader. So here I'm going to go to my PP outline shader. I'm going to press Ctrl and space on my keyboard, get the detect edges normal here. I'm going to right click on thickness, promote to parameter, I'm going to rename it to thickness normal outlines. I'm going to put a default value of 1.6. Then I'm going to right click on threshold, promote to parameter. I'm going to rename it to threshold normal outlines. I'm going to change its default value to 1. Okay, and here, if you want to combine this edge detector with the code we did earlier, we just need to add another lerp with the color we want to apply to the edges that it detects. So here, I'm going to right-click, type linear interpolate, take this one. I'm going to plug it right here and plug it right here. I'm going to right-click, type vector parameter. I'm going to type color normal outlines. I'm going to plug it right here and plug it right here. So what we do here is that if the alpha, so if we detect an edge, the alpha will be equal to 1 and we'll change the color of the pixel to black. If not, we are going to get the result from the first linear interpolate node right here. So if the depth edge detector already detects an outline, this will return black, and this will turn it to black again if you find an outline or not. So that's it. If you go to the viewport, save and apply, go to the viewport, open the PPI outline shader, you will see that everything works correctly. So here you have outlines. If you change the thickness of the depth outlines to 0, you will see that we have outlines related to the normal of the character. If we change the thickness of the normal outlines, you will see that we don't have outlines anymore. So we can put it back to 1.6 and 2. And that's it. So here you have the base version of our outline shader, but now we'll start adding complex functionalities to it to have the cleanest and most customizable outline shader possible in Unreal Engine 5. Okay, so first we are going to tackle a bug that happens with the depth edge detection. If you try to look at a surface from an angle that is close to being parallel to this surface, let's say right here, our shader tends to detect a big portion of it as an edge. This problem is due to the fact that the more our angle of view is parallel to a surface, the farther the pixels of the same surface become from each other, which in turn is interpreted as being part of an edge. So to fix this problem, we are going to create a new material function. I'm going to press F11 on my keyboard, go into the functions folder, right-click, select materials, you know the drill, select material function, rename it to mf_dtm for depth threshold modulation _ grazing angle. The grazing angle is when you look at a surface from an angle that is nearly parallel to it. So here I'm going to open it. And this function will return a value that will be multiplied by the depth outlines threshold to modulate its value based on the normal of the surface. So here, to be more precise, this function will make it so the more the surface's normal is perpendicular to the camera view vector, the greater the depth discontinuity between pixels of the convolution kernel will need to be considered as an edge. And to be able to make something like this, we are going to use the Fresnel node. So here in my grazing angle function, I'm going to right-click, type Fresnel. Here, the Fresnel. I think he's a French guy. I'm going to plug the output here to the output result. And here, if I save, you will see something interesting in the viewport right here. So here, the Fresnel node works as follows. When a surface looks directly at the camera, for example, this is the case for the inner part of the sphere in this viewport, it returns a value of 0. In other words, a black color is output. On the contrary, the more a surface normal is perpendicular to the camera, which is the case for outer parts of the sphere right here, the more the output value gets close to 1 or close to a color of white if you are talking about colors. And there you go. Thanks to the Fresnel, we have our detector for parts of the scene where the surface is parallel to the view angle. But before moving on to the next part of the tutorial, and since we want to have more control over the result, we are going to add more customization to this function so that we can adjust the output of the Fresnel node. So first, we are going to add a parameter that will help us control the fall-off from 1 to 0. So here we have a fall-off from 1 to 0. I'm going to right-click on exponent in, select promote to parameter, rename it to Fresnel power, set its value to a default of 5. Okay. And here, the bigger this value is, the faster the fall-off from 1 to 0 or from white to black occur. So here, if I have a value of 5, you will see that we have this fall-off from white to black. If I put a value of 1, you will see that the fall-off occurs more slowlier. So I can put a value of 5 here. After this, we are going to add even more customization with a few more nodes. So here I'm going to add something. I'm going to add a little formula. I'm going to drag a wire here, type subtract, okay, subtract 1. Then I'm going to add a divide node. I'm going to right-click on the B parameter, select promote to parameter. I'm going to rename this parameter to grazing angle mask power. I'm going to set its value to a default value of 1. Then I'm going to add 1. And finally, I'm going to add a saturate node. Okay, that's it. So here what we do with this formula is make it so the bigger the value of the grazing angle mask power is, the slower the fall off from 1 to 0 occurs. So just so you know here, the saturate node works like a clamp node which prevents the result from going below 0 and above 1. So we can understand it more easily when we look at the variation of the power, this value, with an online tool called GraphToys. So here I have this formula that I've inputted right here, and here you have the power, the grazing angle mask power. So here you can see that if I have a value of 0.5, the curve goes from 1 to 0 at a speed that is relatively high. If I increase this value to 0.5, it goes slower from 1 to 0. If I put a value of 1, it goes even slower, and the bigger it gets, the slower it falls from 1 to 0. So now that we've adjusted the output of our Fresnel node, we can multiply this value by a modulation factor to increase its effect on the scene. So here I'm going to add a multiply node, and then I'm going to right-click on the B input, promote to parameter, type grazing angle modulation factor. So the bigger it is, the bigger the threshold will need to be. So here I put a default value of 1 or 10, let's say 10 here. And also, now that we have it, we don't want our function to output a value below 1 because it will reduce the threshold and draw outlines everywhere. So to prevent this from happening, we are just going to add 1 to the result before returning it, so that when we multiply its value by the threshold, it will return a value which is equal or greater than the threshold. So here I'm going to add 1. And voila. Now that our function is finished, to make it work, we just need to multiply the depth outline threshold by its output. So here, I'm going to go to the PP outline shader. I'm going to go to the depth edge detection method right here, the DO. And here in the threshold, I'm going to disconnect it by clicking on Alt on my keyboard and left-clicking right here. I'm going to add a multiply node. And here, I'm going to press Ctrl plus space on my keyboard, get the DTM grazing angle, plug it right here. Here I'm going to right click, type switch parameter. I'm going to type grazing angle modulation. The multiply, I'm going to plug it here in true. And if we don't want the grazing angle modulation to occur, we get the threshold right here and plug it to false. I can save it. If I go to the viewport and go right here, let's say right here, if I open my PPI outline shader and activate the grazing angle modulation, you will see that these artifacts will disappear. So here I activate it. Oh, no more artifacts. So as you can see, our outline shader just got cleaner. So if you still have artifacts in extreme conditions, let's say right here, you can increase the grazing angle mask power, modulation factor, excuse me, to 20 or 30, depending on your needs. So here I can put value of 50, even 100, and you will see that we have the cleanest outline shader possible. Okay, so that's great and all, but if we go far away from the scene, we can see that some of the actors become completely black. Here you can see these ones. And this is due to the fact that since outlines are created directly on the texture of the screen, they keep the same thickness for an object that is really close to the camera and another one that is really far. So what we want to do here is to make it look like outlines are drawn in the scene and therefore become thinner for objects that are far away from the camera and thicker for objects that are really close to the camera. To do this, we are going to create a function that returns a thickness based on the current depth of a pixel. If the pixel is located directly on the camera at depth 0, the outline stroke will have its maximum size. Let's say if we go really close to an edge, and then the farther we get away from the camera, the smaller the stroke will become until it reaches its minimum size at a defined maximum distance. So here I'm going to create a new function, right click, select materials, material function, rename it to mf_thickness modulation. I'm going to open it. And here first I'm going to create the inputs we'll need for this function. I'm going to right click, type function, function input, change it to max thickness, change its value to a type of scalar, add a preview constant of 2, okay, and this parameter will represent the thickness that outlines have for an object that is at depth 0, so the biggest size of the outlines you have when you are really close to an object. So here I'm going to duplicate this, Ctrl+D on my keyboard, rename it to min thickness, put a value of 1 as a preview, and this input represents the minimum thickness that an outline can have when the pixel is at a distance equal or bigger than a given maximum depth. And here I'm going to duplicate it and create this max depth value, put a preview of, let's say, 5000, and this last input will represent the distance at which the thickness of the outlines becomes the thinnest possible and stops getting smaller. Okay, so now that we have our inputs, let me try to explain to you how this function will work in the simplest way that I can. So here I have this presentation, so I won't go into details, but just so you know, to create this function, we need to find a negative linear function that has the form of a times x plus b that, for a given depth, will output a corresponding thickness. So since we know we want the thickness to be equal to its maximum value when we are close to the camera, in other words, at depth 0, and since we also know that we want the thickness to be equal to its minimum value when we are at max distance from the camera, by solving the equation, we get this negative linear function that we can use in our outline shader. So here, I'm going to disappear, and you have this function that we are going to implement in our shader. Okay, so now that we have everything we need, we can implement it like this. So here I have the max thickness, and here the min thickness. I'm going to subtract the min thickness by max thickness. Then I'm going to divide the result of this by the max depth here. Then I'm going to multiply this value by the scene depth, so the current depth of the current pixel. And here I'm going to add this to the max thickness so that we have our formula that is completed. Again, don't mind the error. So here, before moving on to the next part of the tutorial, we need to add something else to our function. So since this is a linear function, if the depth of a pixel, so this value goes above max depth, the maximum depth here, it will result in a thickness that is thinner than min thickness. So to prevent this from happening, we are going to add a min node so that the scene depth won't go above the max depth allowed. So here I'm going to drag a min node. So here, if scene depth goes above max depth will be outputted right here to the B input. So that's it. Now we can call it in our outline shader. I'm going to save it, go to my outline shader, and here in the detect edges depth, I'm going to add, press Ctrl plus space, add my MF thickness modulation. I'm going to plug the thickness DO to max thickness here. The min thickness, I'm going to right click, press promote to parameter. I'm going to rename it to min thickness depth outlines. I'm going to put it to a value of, let's say, 0.51. The max depth, I'm going to right click, press promote to parameter, rename it to max depth outlines. I'm going to put it to a value of, let's say, 2000. Then here I'm going to right click, type switch parameter. I'm going to rename it to thickness modulation. If it's true, so you want modulation of the thickness, we plug it right here. If it's false, we'll put the default thickness. So here I'm going to plug it right here. Then I'm going to do the same for the normal edge detection part. Here, the thickness, I'm going to get it. I'm going to duplicate it. Here I'm going to plug the thickness right here, right click, promote to parameter. Doesn't want to make, well, let's see, a scalar parameter. I'm going to type max depth normal outlines. I'm going to put it to a value of 2000. Here, max depth. Then I'm going to right-click scalar parameter, scalar parameter. I'm going to rename it to min thickness, normal outlines. I'm going to put it to a value of, let's say, 0.51. Plug it in min thickness. And here in the false, I'm going to plug the thickness. Finally, this result, I'm going to plug it in the thickness of the normal edge detector. So here, if I apply and save and go to the viewport, if I get the PPI outline shader, if I go far away from these characters and activate the thickness modulation right here, you will see that everything works correctly, except that we have a small bug that we need to fix, and we'll see in the next part of this tutorial. If you try to use our thickness modulation function in every case possible, you will find that there are some cases where it doesn't work correctly. So here you can see an edge case where outlines are placed between surfaces that have three various depths, 20, 500, and 5000. This results in inconsistent outline thickness, which is obviously something that we would like to fix. So here we have inconsistent outline thickness. This is big, and for the same object, this becomes small. So why does this inconsistency happen? It's easy to understand. Since the shader goes through every pixels of the screen, each of them has its own depth and therefore its own thickness. To fix this, we are going to modify our shader so that instead of taking the depth of a pixel to define the thickness of the outline, we are going to use a convolution kernel and get the depth of the pixel of the kernel that is the closest to the camera. This way, the thickness of an outline will be based on the object that is the closest to the camera and therefore put a bit of consistency in the outlines. So doing this will be extremely easy. I'm going to open my MF thickness modulation, and all you have to do here is add these nodes to the graph. So here I'm going to press Ctrl plus space. I'm going to get a kernel here. Then I'm going to get the max thickness input right here. I'm going to plug it in the width right here. Then I'm going to duplicate the scene depth 4 times right here. Put it center, left, right, up, and down. And from this, I'm going to extract the pixel of the kernel that is the closest to the camera by calling a min node. So here, min, right here, min. I'm going to get the min depth of between all the pixels of the convolution kernel. So here I have this one. And this way, the thickness will be defined on the object that is the closest to the camera. So here, if I go to the viewport, if I place, let's say here, a sphere, right here, let's put it like this. If I open my PPI outline shader and put a scale that is really big, let's say, for example, a max thickness, let's say 5 and 5, you will see that there is consistency in the thickness of the outlines. Okay, so now that our thickness modulation function works as expected, we are going to tackle another problem. So here, if you place a sphere in the scene, let's say a sphere right here, put it really far away from the scene, let's say 80,000, give it a big scale, like 200, for example, to make it look like a planet, you will see that our shader will draw outlines on it. So maybe you want it to look that way, but if you have a skybox or a sky sphere in your scene, usually this is something that you want to avoid from happening. And to do so, we are going to add depth masking to our outline shader to make it so objects that are too far away from the camera won't have outlines. So here I'm going to create a new function, right click, material, you know the drill, material function, rename it to mf_mask_depth, and open it. So this new material function will be quite simple to implement, since we want it to return 0 if a pixel is farther than a defined distance, and 1 if it's closer than this distance. So first, I'm going to create an input, right click, function input. I'm going to rename it to max depth, okay, change its type to scalar, put a preview value of, let's say, 100,000, for example, here. And this input will represent the max distance at which we want our shader to draw outlines. Then I'm going to use the step node we used earlier, here, plug in a scene depth node. And this will make it so the step node will output a value based on the comparison between the max distance and the depth of the pixel. So here, if the depth of the pixel is equal to or bigger than max distance, the step node will return 1 and 0 otherwise. However, since we want the exact inverse, we are going to use the 1 minus node. So here we are going to call the 1 minus node. And doing this will make it so when the step function returns 1, it will return 1 minus 1, which equals to 0. And when the step function returns 0, it will return 1 minus 0, which equals to 1. So here I'm going to plug it right here. And that's it. Now let's try to add it to our outline shader. I'm going to save, go to my outline shader. And here I'm going to add it to the depth edge detection method. I'm going to get this here. I'm going to press Ctrl space on my keyboard, get the mask depth, drag it into the graph, right click on max depth, promote to parameter, rename it to max drawing distance. I'm going to set it to a default value of, let's say, 500,000. Then I'm going to multiply its value by the value of the edge detector. I'm going to add a new switch parameter, rename it to depth masking. In the true input, I'm going to plug the result of this multiply node, and in the false, if we don't want depth masking to occur, we plug it in the false pin. So here I'm going to plug it into alpha, and I'm going to add it to the edges detector based on normal. So here, let's see this one. I'm going to press Ctrl space on my keyboard, get the mask depth. I'm going to duplicate the max drawing distance, Ctrl plus D. Since it's the same parameter, we would like to apply it to both the detection method. Then I'm going to multiply its result by the edge detector based on normals. I'm going to duplicate the depth masking switch parameter. Here, in the true, I'm going to plug the result of the multiply. In the false, the result of the edge detector, and plug it in the alpha. So here, if this is activated, if the pixel is farther than max drawing distance, this will not draw outlines on it. So this will return a value of 0, which multiplied by the value of the edge detector will return 0, and therefore not draw any outline. So now if we go to the viewport and activate our depth masking right here, you will see that this sphere will no longer have outlines. Whoop, maybe it's too close. Let's say max drawing distance, let's set it to 50,000. Yeah, you will see here that we do no longer have outlines on the sphere that is far away from the scene. However, if you try every possible case, you will find an edge case where there's a problem. So funny enough, this is the same case as the one we encountered when we were applying modulation to the thickness, and we can solve it with the same solution. So here, the problem is that since this pixel, for example, is part of an edge that is shared by a surface that is close enough to the camera and by another one that is too far away from the camera, this results in outlines drawn on the first object and not on the second one. So here you can see that outlines are drawn here, but since this pixel is far away than max distance, this does not allow the drawing of outlines. So to prevent this from happening, and just like what we've done for the thickness modulation, instead of testing only the depth of the current pixel, we are also going to test the depth of its neighbors to see if at least one of them has a depth that is below max distance. If so, then we can draw outlines on this pixel and keep a consistency between outlines of the scene. Okay, so now that we know how to solve this problem, and since it's the same solution we used earlier for the thickness modulation function, first we are going to open the MF thickness modulation material function. Then I'm going to select this and this. I'm going to press Ctrl C on my keyboard, Then I'm going to go back in my mask depth material function, and I'm going to press Ctrl V to paste the result over here. So here I'm going to select this. I'm going to plug it here in the step, remove the previous scene depth node, and there we go. And before trying it in the viewport, we need to go to the outline shader, PP outline shader, and we need to plug the max thickness right here that you can see, the new output that we've just created. We need to plug the thickness modulation right here to max thickness for the normal outlines, and go to the depth outlines and plug the same thing. So here, thickness modulation, I'm going to plug it in max thickness. So here I'm going to save and apply. And if I go to the viewport, we can see that everything works as intended. Okay, so now the next functionality we are going to add to our outline shader is the ability to draw outlines only on some of the actors of the scene. And to do so, we are going to use what we call the custom depth buffer. And for those of you who don't know what the custom depth buffer is, you can see it as an additional depth buffer in which you can choose what actors of the scene you want to sample. And to better understand how it works, if you go in the viewport here and enable the custom depth visualization by going over there on lit right here, you can go to buffer visualization and select custom depth. You will see that the screen becomes completely black since nothing was added to the custom depth buffer. If you want to add an actor to the custom depth buffer, it's easy to do since you just have to select it in the viewport. Let me try to select a character. Okay, this one. You can go here in the details panel and search for custom. And here you can enable the render custom depth pass option. You can check it. And as soon as I check it, you will see that the character will appear in gray. So here, if I select this one and the two other ones right here, and go to render custom depth pass and check it, you will see that the selected actors became gray, which means that it has successfully been added to the custom depth buffer. To make our system work, we are going to sample the custom depth buffer and draw outlines only on actors that are added to it. So here I'm going to create a new material function. I'm going to put myself on the right side of the screen. Right click, select materials, material function, rename it to mf_mask_custom depth. Then I'm going to open it. And here we'll try to sample the custom depth buffer in our shader. It will work exactly the same as a depth buffer, except that it will return the depth of a pixel only if it's present in the custom depth buffer. On the contrary, if a pixel is not present in the custom depth buffer, it will return a depth that is really big, like 100,000, for example. So knowing this, you will see that it's extremely simple to implement this functionality in our shader, since it will work roughly the same as the depth masking function we've just created. And to demonstrate how fast it will be to implement this function, I'm going to open my mf_mask depth function. I'm going to select all the nodes, these ones. I'm going to press Ctrl+C on my keyboard, go in my mf mask custom depth, press Ctrl V to paste everything. And here, I'm going to plug it right here. And for the scene depth, I'm going to remove all of it, add a scene texture node. And to be able to sample the custom depth buffer, it's easy. You can go here to scene color and select custom depth. So here I'm going to plug the center, duplicate it 4 times. Here, left, right, up and down, up and down. Here, then I'm going to plug the color pin here, here and here. And there you go. That's it. So now that we have it, just so you know, here we use a convolution kernel because if we don't do so, we will see inconsistency in the outlines around an object if it shares screen space with an object that is in the custom depth buffer and another one that is not. So now that everything's okay, we can add this function to our shader by going to the PP outline shader right here. And in the depth edge detection method, I'm going to add something right here. Depth masking. I'm going to right click, switch parameter, custom depth masking. I'm going to get this, plug it right here. If we don't want custom depth masking, we can use the depth masking right here. Then I'm going to press Ctrl plus space on my keyboard, get the mask custom depth right here. And just like with the max depth right here, I can plug the max thickness here, max depth here if you want the same one. You can create another parameter if you want a specific one for your custom depth, and plug it, multiply, plug it to a multiply, and then multiply this value by this one. Then I'm going to duplicate this custom depth masking and do the same in the normal edge detection method. So here I'm going to get this, plug it here, this one plug it over there, this here. The thickness, I'm going to get the thickness modulation right here, and the max drawing distance, I'm going to plug it in the max depth. So here, if I save and apply, if you go in the viewport, and then you can select the PPI outline shader and activate the custom depth masking, you will see that outlines are drawn only on these characters since they are in the custom depth buffer. However, here we have yet another problem. If you place an actor that is not placed in the custom depth in front of an actor that is placed in the custom depth, you will see outlines appear where they overlap. So here, to better show you how it works, if I change the outline color to red, here, put the same color for normal and depth outlines. If I get this actor which is not in the custom depth and place it in front of the other actors, you will see that some parts of the actor have outlines applied to them, as if it was in the custom depth buffer. So here, to prevent this from happening, we just have to add something else to our function. So here I'm going to go to my custom depth mask function, and I'm going to apply a new piece of code by duplicating this part here. Press Ctrl C, Ctrl V. I'm going to plug it right here. Then I'm going to select these nodes in custom depth scene texture nodes. I'm going to change them to scene depth. Then I'm going to get the output result, call an if node, plug it in the output result. I'm going to get this min and plug it into the B input. Take this one, this min, into the A input. Then I'm going to add a constant 0, plug it into A greater than B and A smaller than B. And then I'm going to get this value and plug it in here. So here, doing this will make sure that we draw outlines on a pixel only if it's the one that is visible in the default scene buffer. Okay, so let me give you a quick note before moving on to the final functionality we are going to add to our outline shader. Here, as you can see, our outline shader is becoming bigger and bigger over time. Of course, here I'm adding a big amount of customization to it, but if you don't need all of these functionalities for your specific project, I strongly encourage you to remove the unused functionalities so that your shader will become less complex and more optimized for what you're trying to achieve. Anyway, let's move on to my favorite functionality of them all, the multi-colored outlines. So now that we know how to choose the actors of the scene on which we want to apply outlines, we are going to go even further by adding the ability to change the color of the outlines on a per actor basis. So first, I'm going to show you the method everyone uses on YouTube to make multicolored outlines, and then I'm going to show you my method for doing this, which will go even further and prevent you from writing a lot of code in your shader. So in the previous section, we learned about the custom buffer, which is an additional depth buffer in which you can choose what actors of the scene you want to sample. Here we are going to use another cool functionality of the engine, which is called the Stencil buffer. You can see the Stencil buffer as an array composed of 255 custom depth buffers, and just like with the arrays we use in Blueprints, each of these Stencil buffers has an index assigned to it going from 1 to 255, 0 being the index of the default custom depth buffer. Okay, so now let's say we want an actor of the scene to have blue outlines and another one to have red outlines. What we are going to do is store the first actor in the Stencil buffer that has an index of 1, and the second actor in the one that has an index of 2. Then in our shader, what we're going to do is test if an actor is in a stencil buffer, and if so, we are going to apply blue outlines on it if the index of its stencil is equal to 1, and red outlines if the index of its stencil is equal to 2. Okay, so before being able to use the stencil buffer, we need to activate it in our project settings. So here I'm going to go to Edit, then Project Settings, and here I'm going to search for Stencil. Here you will see the option Custom Depth Stencil Pass. You will select Enabled with Stencil. Then you can close this. And now if you go in the viewport and enable Custom Stencil Visualization by going here on Lit, Buffer Visualization, and select Custom Stencil, you will see that everything becomes black. To put an actor in a specific stencil buffer, we're going to select it. Let's say this one. Here on the right side of the screen, I'm going to search for Custom. And here, just like with Render Custom Depth Pass, you will need to have Custom Depth Stencil value and put it at a value that is greater than 0. Let's say 1. 1, for example. Then I'm going to select the second one, another character. Where is it? Here, it's here. I'm going to put a value of 2 right here. And here I'm going to select the third one, which is around here, and put a value of 3. Okay, so here you can see the stencil value assigned to each actor, and we are going to use it to implement in our shader. So we have a stencil value of 1 for this one, and stencil value of 2 for this one, and a stencil value of 3 for this one. So here I'm going to go back to my lit mode. I'm going to create a new material function. I'm going to the right side of the screen, right click, material function. I'm going to name it mf underscore get stencil based color. Get stencil based color. I'm going to open it. And here in this material function, this will output a color for the outlines of an actor based on the index of the stencil it is a part of. So first we need to get the custom stencil buffer index in which the actor is and extract its index. So here I'm going to right click, type scene texture. And here you can see on the scene texture ID that we have access to the stencil custom stencil right here. Okay, so here the color output contains the index of the stencil. However, since it's a color, it's like a vector and has 3 components: red, green, and blue, each having the same value, the index of this stencil. So to work with a float, we are going to extract only one of these components. So I'm going to drag a wire from the color and type component mask to get only the red channel right here. I'm going to check only the red channel. Okay, so now that I have this, I just need to compare this to a value to decide which color we want to apply to the actor. So here we are going to assign 3 different colors to the actors of the scene, and I'm going to press V on my keyboard and click to add a vector parameter. I'm going to call it color 1. I'm going to duplicate it, rename it to color 2, and duplicate it again and rename it to color 3. Then I'm going to compare this value. So here I'm going to add an if node. I'm going to plug it here, this one right here, and then I'm going to compare it to a value of, let's say, 1. If the stencil is equal to 1, then we are going to set the color 1. Then I'm going to use another if node. I'm going to put here a value of 2, plug it right here and right there, because we only want when the value is equal to 1. Here we are going to compare the value to 2 here. If it's equal to 2, we are going to set the color 2. And if it's not equal to 2 or equal to 1, we are going to set a value of a color of 3, the color 3. So here I'm going to select a color for each of these parameters. I'm going to put a pink value right here and a green value right there. I'm going to apply, save, and then I can implement this function in my outline shader. So here I'm going to my PP outline shader. I'm going to go to the depth outlines here first. I'm going to right click, type switch parameter. I'm let's say multi-color. I'm going to press Ctrl plus space on my keyboard, get the get stencil based color, plug it in here, plug it in there, and this one right here. So I'm going to put its default value to true. Then I'm going to select this, press Ctrl C, go to my normal outlines here, Ctrl V, plug it here, and plug it this one here. Then I'm going to apply. And now, if we go to the viewport and activate the multicolored outlines, you will see that everything seems to work, but there's a small problem, as usual. Okay, so here if you watch closely, you will see that the actors of the scene seem to have two layers of outlines, one with the color specified in the shader, and another one set to the third color, which is the green one. The reason why it happens is, just like with the thickness modulation, due to the fact that we sample the stencil on a per pixel basis. And to make it work like we want, we're going to use the same logic we used earlier to fix the thickness modulation bug we had earlier by getting the convolution kernel around the current pixel and extract the stencil value of the closest pixel. Since we need to get the coordinates of the closest pixel of the kernel, the code will be a bit dense compared to what we've done earlier, so please bear with me. So here, I'm going to open my function get stencil based color, okay, and here we are going to get the convolution kernel based on the desired outlines stroke thickness. So here I'm going to press Ctrl space on my keyboard, get the kernel, add an input, function input. I'm going to set it to scalar and call it thickness. I'm going to plug a preview value of 1 here. And now we are going to create a small function that will compare the depth of 2 pixels that are in the custom depth buffer and return the coordinates of the closest one. This will help us create a cleaner code. So here I'm going to press Ctrl space on my keyboard. I'm going to create a new material function. Right click, material, material function. I'm going to rename it to mf_compare custom depth. I'm going to open it. And here I'm going to create 2 inputs that will represent the UV coordinates of the 2 pixels we need to compare. So here I'm going to right click, function input. I'm going to set it to a float 2 right here. I'm going to rename it to UVA. Okay, I'm going to plug a default value of 0, 0. I'm going to duplicate it. I'm going to rename it to UVB. And there we go. So now we are going to sample their depth in the custom depth and extract a float from that. So here, I'm going to call scene texture. I'm going to get the custom depth. Custom depth, where are you? Here. I'm going to duplicate it here. And I'm going to extract only a float value like we did earlier. So here, I'm going to get component mask, extract only the red channel, okay, duplicate it, and now we can compare these two. So why do we use the custom depth instead of the standard depth buffer? It's because if we want to use our custom stencil, the actors are necessarily present in the custom depth buffer. This will help optimize our code and a bit, since it's, instead of sampling the entire custom depth, we just sample what's in the custom stencil. So now that we have this, we can finally compare the 2 depths and output the coordinates of the pixel that is the closest to the screen. So here I'm going to call an if node. I'm going to compare these 2 values here and here. And if A is greater than B, this means that the B is closer to the screen. So we will output the B value. If A is smaller than B, this means that A is closer to the screen than B, and we will output A. Now we just have to plug it to the output, and there we go. We can apply it, save, and we can go back to our stencil-based color. So now we can use the new function we've created here to extract the coordinates of the pixel that has the smallest depth. So here I'm going to press Ctrl space on my keyboard. I'm going to get compare custom depth. And then I'm going to compare this one to this one. I'm going to duplicate it, compare this one to this one, duplicate it, compare this one to this one, and this one to this one. By doing this, we extract the coordinates of the pixel that has the smallest depth of all the pixels of the kernel. So when we get this coordinate, we can plug it in the scene custom stencil and therefore get the index of the pixel that is the closest to the screen. So now, if we apply it, we need to go to the PP outline shader. Since we've created a new input for this function, we are going to plug the thickness modulation right here and the thickness modulation in the depth outline detector. This one right here. Get stencil based color. So now you can apply, save, and there you go. If you go in the viewport, you will see that the outlines are drawn correctly on the object and that when objects overlap each other, the outline color of the object that is the closest to the camera is picked. So I can bring back my size, my outline size to its default value, and you will see that everything works as intended. Okay, so now that you know the gist of how the custom stencil buffers are used to define outlines colors on a per actor basis, I'm going to show you a way to get around 255 different outline colors without having to add an if node in the shader for each color you want to add to your palette. To be able to do such a thing, we are going to work with the hue. If you don't know what I'm talking about, I'm going to open a color picker, and here you have the color with the hue value available right here. Okay, the hue is right here. Here, if I turn around the color disk, you can see that the hue changes from 0 to 360. Just so you know, red is the color that has a hue equal to 0. And if we make a shift by 200, in other words, if we go to a hue of 200, we land on the cyan color. What we want to do here is to make it so each stencil buffer has its own color assigned to it based on the value of its index by breaking 360 into 255 chunks. This way, if a pixel in the custom depth buffer has a stencil index of 1, its outline color will be red. And if another one has a stencil value of 88, when converted to a hue, it will correspond to a hue of 124, which is the color green in the color picker. To make this system work, we are going to apply some modifications to the getStencil-based-color function we created earlier. So here I'm going to open the getStencil-based-color material function that we created, and here I'm going to remove these nodes because we won't be needing them anymore. So I'm going to delete these ones. Then to make the hue shift, we are going to use the hue shift node. Here, right click, I'm going to type hue shift, and I'm going to get the hue shift node. To make this node work as intended, it needs to have a texture or a color as an input. Since we are going to shift the hue from a red color that has a hue of 0, we are just going to plug in a red color. So here I'm going to right click, type constant, get the constant 3 vector. I'm going to put a value of 1 right here in the red channel to have a red color, and I'm going to plug it in the texture right here. Then we want to be able to change the value of the color, in other words, its shininess. To be able to do this, we are going to multiply the red color by an emissive factor. Multiply, plug this right here, right click, promote to parameter, and call it a stencil color emissive factor. I'm going to put its default value to 1. And finally, as for the hue, we have a bug here. Finally, as for the hue shift percentage parameter, instead of getting a value between 0 and 360 as an input, it needs to have a normalized value between 0 and 1. To do so, all we need to do is divide the stencil value by 255 and plug this in this input. So divide this one by 255 here and plug this in here. Now I just need to plug this in the output result, and voila. If you go to the viewport and select an actor, let's say this one, if you change the stencil value, so let me put myself in the middle of the screen, if I select the stencil value and move it, you will see that I can change the color of the outlines for each actor. So also, if you want to make the outlines glow more, you can go to the PPI outline shader and you can search for the stencil color emissive factor, this one. If you want to get black outlines, you just have to put a value of 0 for this one. If you want to increase the shininess of the outlines, you can increase it to 20, let's say 50, 100, 1, 2, and you can play with this value to get the effect that you want to get. However, I think you know the drill, we have a problem. Okay, so it's not really a problem, but I think we can agree on this. If I want a specific outline color, let's say yellow, for example, I have to scroll through every stencil value possible to find the color that I want. It's not ideal, and in this section I'm going to show you how to create a tool that gives the ability to interactively change the color of the outline for each actor of the scene. And to be able to achieve something like this, we're going to create an editor utility widget that will allow us to select an actor in the scene and set its stencil value based on the outline color we want to apply to this actor. So first, I'm going to create an editor utility widget by right-clicking in the content, go to Editor Utilities, and select Editor Utility Widget. I'm going to rename it to EUW for Editor Utility Widget _ set outline color. So for those of you who don't know, an editor utility widget is a widget that can be called and used in the editor without having to launch the game. So here I'm going to open this editor utility widget. And when you do, you'll see that the interface looks like a default widget blueprint, except that you can work on actors of the scene. So first, we are going to code something that will allow us to convert a given color to a stencil index. So here, I'm going to go to the graph right here. I'm going to create a new variable called color. I will change its type to linear color, this one. And here we created a variable that will hold the desired color we want to apply to an actor that will be selected in the scene. So now that I have this variable, I'm going to drag it in the graph, select get color. I'm going to extract the hue from this color by calling the node RGB to HSV here. And here we can see that we have a H output that holds the hue of the color variable. Since this value goes from 0 to 360, we are going to use the cross multiplication to convert it to a value that goes from 0 to 254. So here I'm going to divide by 360. Okay, so it's cross multiplication. And then I'm going to multiply this value by 254. Okay, so now I have a value that goes from 0 to 254. Then I'm going to add 1 so that it goes from 1 to 255. Finally, I'm going to get the integer part of the float by calling the truncate node. Why the integer part? Because the stencil buffer is defined as an integer. So here I have a stencil buffer index from a desired color. Okay, so now that we know how to convert a color, we need to be able to get the selected actors to be able to change their stencil value. And thanks to the fact that we are in an editor utility widget, we can do it easily by calling the get selected actors node. So here it has all the actors that we selected in the scene. So here, if I select this one, this will output this actor. This will output both the actors. This is why we have an array. So now that we can get all the actors of the scene, we want to be able to change the stencil on each of them by first calling a for each loop. So here I'm going to drag, I'm going to call a for each loop. You will see that this is a bug that we have with editor utility widget. And to be able to call a for each loop, I'm going to press Control space. I'm going to open, let's say, any blueprint, this one, let's say a third-person character. I'm going to call a for each loop right here. I'm going to select it, cut it, Control plus X on my keyboard. I'm going to go over here on my editor utility widget and paste it here. So here I have a for each loop. Epic Game, if you're watching this, please fix this bug. And so to be able to apply this on each actor, I've used a for each loop. And now we would like to change the stencil value on the selected actors. But since a custom depth buffer is available for static meshes and skeletal meshes only, for each of the selected actors, we want to get only these types of components. Lucky enough, skeletal meshes and static meshes are subclasses of the primitive component class. So here I just have to call a get components by class, and here I just have to search for primitive component. This one, primitive component. Finally, now that we can get the primitive components of an actor, we can go through each of them. So I'm going to drag it and see the magic of this. If I drag a wire from here and type for each, this time it works because I have this one in here. I don't know why it works like this, but this works. I'm going to plug this right here. And for each of these components, I'm going to activate the render. So set render custom depth. Okay. I'm going to activate the custom depth render pass. And I'm going to change the stencil value by calling the node set custom depth stencil value. I'm going to plug here, I'm going to plug the result of my formula, and there you go. Here we get all the actors that are selected, and for each of them we get all the components that are of type static mesh or skeletal mesh, and then we apply custom depth on these and change their stencil value based on the color we want to apply. Okay, so now we have this. The question is, when should we call this piece of code? You can do it with the press of a button, of course, but I figured out it would be cool to just select an actor, call a color picker, and directly change the color of the outline with this color picker. So to be able to do something like that, we are going to add the ability to change the value of the color parameter, so this one, of our widget directly from within the editor. So here I'm going to go to the designer part of the editor utility widget. I'm going to remove the canvas panel, select it and press delete on my keyboard. And then I'm going to add, let's search here in the palette for details view. I'm going to add a details view to my hierarchy. So I'm going to drag it right here, and you will have the undefined object problem. Okay. So the details view widget allows us to see and modify the variables of this widget, of this editor utility widget. To make it work, I'm going to go to the details tab right here. Then in the view category, right here, I'm going to add an element to the properties to show array. Here, properties to show. Okay, you have this one. I'm going to add an element, and I'm going to give the same name as the color variable. So here, color, I'm going to press F2 on my keyboard, copy, go to the designer, and paste its value here. So here, properties to show, we have added an entry which is called color. Okay, so now, having the color view widget selected, I'm going to add a call to the onProperty changed right here. Oh, you don't see it, it's small. You have the onProperty changed. This dispatcher right here, onProperty changed. Okay, you have to click on it, and this will appear in the graph. So this event will be called every time the property changes. So if the color changes, it will call this function that you have right here. So I'm going to link it right here. I can delete these ones. And now I can compile and save. And finally, to make the details view widget work as intended, I'm going to set the object on which it's going to fetch the color variable. So here we told it to get the color variable, but we didn't tell it where it should get it. Should it get this value on an actor in the scene or on anything else? Here we want to get this value on this actor, on this editor utility widget. So here I'm going to go to the graph. I'm going to right click event pre-construct. I've just deleted it. And here I'm going to get the details view. I'm going to set object, and I'm going to plug in a self value. Now that everything's okay, you can compile, save, and voila. If you go in the viewport, right-click on the editor utility widget, then select Run Editor Utility Widget, it will open this small window. Then all you have to do is select an actor in the scene, click on the color, change the color to the desired color. And here you can see that it works like a charm. So I can change the color of any actor in the scene to any outline color that I want. Let's say purple one. And there you go. You have the cleanest and most customizable outline shader I could create in Unreal Engine 5 in around, let's say, maybe 1 hour. I don't see how long it took. And that's it for me. I really hope you liked what we've done here. And if you want to learn more about Unreal Engine 5, you can click on this video and I will see you over there. On the Dino, on the UE4 mannequin, tackle, able to upline. 5,000. It's over 5,000.